In this video, I look at how one might use simulation to design building commissioning regimes, as well as establishing as-built facade performance. I find myself returning again and again to how practitioners gain trust in their models, as well as the nagging question of why models, which seem to be adequate for answering the usual suspect performance questions, are frankly rubbish when it comes to tracking the minute-by-minute conditions I measure in rooms. The task of getting a model fit for purpose can draw from a number of sources. One of my go-to resources is, believe it or not, Annex 71. It tasks researchers to create fault-free simulation models from available documentation and run very specific virtual experiments. The predictions were later compared with measurements within two houses that had undergone the same experiments. And a budget for an exquisite set of sensors. Goodness, don't I wish. It's a classic validation approach. It includes attention to detail. All the sources and assumptions are documented. QA raised up on a pedestal. Uncertainties identified. Oh, well, but wait. If we take away the double-bind method they used, what remains might be what folks call best practice. Of course, few of us have such resources. I, for one, am glad there are folks out there that like validation. I just wish validation wasn't quite such a glacial operation. At a rather more pragmatic level, we've got co-heating methods. These use an experimental regime to arrive at an overall performance of as-built facades, and they actually have quite a few proponents. Niggles, though. Co-heating typically ties up a building for weeks, produces an aggregate rather than a room-by-room performance metric, and it says not very much about how buildings respond to environmental controls. Being a numerical guy myself, well, numerical methods aren't really central to co-heating. It's not all that helpful in terms of supporting the generation of a well-calibrated, fit-for-purpose simulation model. This slide from a conference presentation sums up the driving forces for developing what I would call a hybrid approach. It takes the best of the analog and provides evidence to allow simulation models to evolve to better capture the characteristics of the building. My go-to resource for joint physical and virtual testing is what I learned during our development with BRE of what I call the pulse test. It's a short duration alternative to co-heating, which we've deployed in several projects around the UK. The experimental rig and sensors are actually quite similar to that used in co-heating regimes. You've got thermostatically controlled convector heaters, fans to stir up the air, surface temperature sensors, air temperature sensors, some clamp meters and watt meters to measure heating, of course data loggers, remote access controls, and the like. Besides the one-week experimental regime, what sets the pulse test apart is a tight coupling with simulation tools and an experimental regime designed to sequentially stress different flow paths within the building as well as within the simulation tool. Simulation is used to design the experimental regime. Where do we want to place the sensors? What's the magnitude and duration of the heating and cooling inputs that we're going to use? What's the length of the pre- and post-conditioning phases? This kind of thing allows the informed deployment of the testing kit in buildings, as well as support for adaptation if site conditions change or there's a fault in the actual experiment. In this slide, here's an initial guess on heating capacity during that design of experiment stage. And, well, its capacity wasn't adequate. And we discovered this in time to order replacement heaters for delivery out to the site. Also in this slide is the pattern that we generally used. We start the building out by tracking a free float towards ambient. This might take 2 or 3 days. And then we do a step change. We kick on the heaters and the fans and capture the response of the building to a step change with approximately a 25-degree delta T to the ambient condition. And again, depending on the building, this might last for 1 to 2 days to get us the near steady state heat flows through the facade. During this time, we identify how much energy inputs are required to maintain the set point in each room. And then we kick the fans and the heaters off and capture, importantly, the response of the building as it returns to ambient. In terms of the simulation model, we tend to represent each room as a separate zone and include any thermophysical clutter we observe. And, well, we want explicit thermal bridges. And we want to leave room for possible construction faults that might be identified in an infrared survey of the building. We want to do a leakage pressure test and then build our airflow network to reflect that. We want our environmental controls set up so that they match the timings and set points of the experiment. Within the simulation tool, it was also necessary to do things like impose high heat transfer coefficients during the fan-on periods. In terms of weather, well, we'd take whatever historical data we could use, but we would make sure, if possible, to collect data on site to actually use during the calibration phase. In terms of calibration, well, yeah, we could have used Monte Carlo techniques and all kinds of fancy things like that, but actually we normally get a reasonable fit by just working through the usual suspects. Beauty of it is that once calibration is done, we've got a simulation model that really represents the characteristics of the building, and then we can use that to further design explorations. Here is one case study house of a terrace house representing different construction epochs. The 1930s epoch was particularly challenging to mount. We presented the pulse test method and this and more case studies at the IBPSA BS 2021 conference in Bruges. And since there are not very many folk that can fit into a conference room, what follows, if you'd like to see it, is the presentation we gave at the conference. And if you find that interesting, you can go on to the IBPSA website and look for the full paper. Hello, my name is John Hand. I'm going to present a paper about a novel testing regime for actual and buildings and their virtual twins. So, there's a tradition of co-heating tests that started in the mid-1980s and considered in various forms since then, which involve injecting heat into a building to bring them up to a specific temperature and then measuring what's the heat or cooling required to maintain that temperature over a long period of time, and then post-processing what's been observed in order to come up with a overall heat transfer coefficient for the facade. The issue with these co-heating tests is that they're lengthy, they're expensive to mount, and they are not particularly designed to interact with simulation. But we also see that simulation models often do not capture the characteristics of specific buildings. They're difficult to calibrate. If we could come up with better tests for actual buildings, which we could then link in and use to calibrate our models, that might be a way forward. So we have talked about a short duration 1-week pulse test regime in the paper, and it's designed to expose the dynamic responses in buildings as well as in their virtual twins across a range of test conditions. The nature of the test, the kit needed, key characteristics of digital twins are explored. Although co-heating has gone on for a considerable amount of time, because there has been a continual need to establish actual heat loss characteristics in buildings, the gap that is often talked about. In the paper, we review the history and characteristics of several methods, including P-star, cube, and co-heating. Most of these involve a site audit and the use of heating or cooling devices to explore how much heat is necessary to maintain a particular set point under varying conditions outside, as post-processing required to arrive at overall heat loss characteristics. Some of the tests are short duration. However, co-heating itself can run for many weeks in order to deliver time-averaged heat transfer. The kit involved in co-heating tests typically involves fans, heaters, measuring devices. Same sort of kit is generally used in the pulse test. We duplicate the primary sensors and logging devices with a secondary system so that we can monitor the experiment as it's actually progressing to see if its status is still good. As with some other pulse tests, we also put foil over the windows in order to limit solar noise. The use of fans to distribute heat also is a good test of simulation heat transfer coefficient methods. We often use additional tests, such as blower doors tests, to calibrate the leakage characteristics of the digital twin, and also, as we're doing it, to highlight faults in the building, which, if corrected, is fine, but if not corrected, we should include in the digital twin. A thermographic study also does several of these same tasks and is particularly good because during the test, the delta T is quite high, and that exposes some faults which are otherwise difficult to see. The problem with coheating often is the need to establish long-term steady-state conditions in a context of ever-changing weather patterns. And there are some aspects of building that are difficult to monitor, such as infiltration rates and particularly the amount of sunlight which is impacting the heating load within the building. The pulse adapts the general idea of coheating with a distinct set of experimental phases for the building and its digital twin. There's an initial stage to drift the building from whatever its initial state is back toward ambient. This might take a day or two. At the end of this, the heat embedded within the building is hopefully neutralized. There's a brief warm-up stage of 8 to 18 hours where we monitor both temperatures and the amount of heat going into each room. We maintain the set point for 24 to 36 hours, again detecting the control actions needed to maintain that set point. And then there's the most important cool down phase, which might be 2 to 3 days, in some buildings maybe even 4 days, where we look at how heat or cooling is released from the building over time. The aggregate model of monitoring of energy needed to maintain conditions in a coheating tends to be a single number. We do it on a room-by-room basis. So, to adapt simulation, first we create the digital twin and then we use it to design the experiment. How long do we need in each of these phases? How much capacity do we need in order to reach our set point? How long is the cool down phase likely to last? And this helps coordinate the timings of the equipment and as well as deployment of staff. The digital twin is, of course, designed to match the experimental regime, not only in terms of the form and fabric, but to mimic the actual test that's being carried out. Actual physical experiments tend to have faults, and so what we've done in the pulse test is notice the nature of those glitches and attempt to include them in the digital twin. The higher level resolution monitoring allows us to look at the divergence between actual and virtual experiments, and that gives us some really good clues as to what specific thing might be wrong in the actual building or in the actual digital twin, and helps us focus our efforts considerably. And certainly the thermographic surveys during the experiment are quite key to identifying faults that need to be accounted for in the digital twin. So here's a case study. There was a terrace house which demonstrates various construction epochs, 1930s, 1950s, 1980s. We ran simultaneously pulse tests on all of these, monitoring minutely heat inputs as well as temperatures. And some of the things that we noticed in our thermographic studies also went into the digital twin. In terms of predictions and measurements, we certainly saw considerable differences between the response of the different epochs in terms of air temperature and surface temperature. For the 1930s epoch, the mass of the masonry within the building was quite apparent, especially in terms of the delay in surface warming and the differences between the resultant temperature in the space and the air temperature, which was the basis of the control set points. Second case study is a new housing development which used essentially 10 different construction types and a regime of 4 different heating schemes. And the client was quite interested in which of these actually worked well, what combinations of construction and heating system worked well together, but were really interested in which ones they should carry forward to subsequent developments. So there was a mix of long-term monitoring, but while the long-term monitoring was going, we also did the detailed monitoring related to a pulse test and carried that out in order to gain confidence in our digital twins so that we could begin to investigate the client's, by way of virtual studies, some of the client's ideas and different combinations. In this case, the dotted lines in the graph are measurements and the solid lines are predictions. And the calibration of the model involved iterations to look at the details of both the actual building and the digital twin. It turned out that this was very good at identifying faults in both of them. It turned out that by correcting the faults, which were in fact the usual suspects, it wasn't actually necessary to go into a formal Monte Carlo-based calibration process. So lessons learned, the design experiment was very valuable in getting insights about what the test how they might progress, as well as noticing faults in the testing. And it also gave us clues about the nature of the buildings and how we could deploy the kit much more efficiently. It certainly provided us evidence to make our digital twin work better. Sometimes we changed the resolution slightly, but this was also a very good test of the simulation facilities on offer. For example, in this particular case, having the fans silent for some parts of the test and blowing at full velocity at others meant that we really needed to upgrade the tool so that we could schedule different heat transfer regimes to match the actual experiment. It's a novel physical and virtual testing regime. We talk about the similarities and differences with classic. We look at how equipment familiar to co-heating practitioners can be redeployed and experiments run in a different way in order to make a better link with the digital side and deliver additional value to clients. We've seen it improves the acquisition and deployment of kit if we've got multiple buildings to do. And it's certainly resulted in a model that could be seen to demonstrate a good fit across a number of classic scenarios in building physics. So certainly a rich source of evidence for judging novel construction techniques, and a check on how well simulation might support such novel techniques. It's intriguing to think about it, to do a pulse test before and after a retrofit to provide evidence that the retrofit actually delivered what was claimed. And we're interested in taking forward the idea that pulse test gives us a much better digital twin, which can use to as perhaps a replacement for expensive long-term monitoring, as well as exploring design ideas for future neighborhoods. Thank you very much. If you've got questions and comments, we can talk about that now.